right, one of the important things that we're going to be learning in this course is how to write and how to write technically, okay? Um, excuse me, I take this rather seriously because I think this is one of the skills that could actually be adapted to anything you do, right? So maybe a lot of you are not going to go into the field of fluid mechanics, but we'll all have to at some point write technically. So I want to go over how we write a lab report and really the stylistic changes we have to do to write technically as opposed to writing a report in English class or something like that. But in the beginning, we're going to just talk about general writing. So this is not specific to technical writing, but things to just remind ourselves. Now, these slides are not the best for presentation or lecture, but the reason I have them set up just as bullet points is I want you to use this as a reference when you're writing your reports. And so I'm not going to talk about every single bullet, but I will just highlight ones that I think are very important. Okay, so a couple of ones here. Make sure that you don't change your tense all the time. And what we're going to see is for technical writing, we're always going to want to be using the past tense when we're talking about the experiment that we did and the data that we had collected. Okay, but we want to make sure that we keep our tense and we don't keep switching. Also check your spelling, and just general proofreading. That's one of the big issues that I've seen throughout the semesters teaching this course, are just not a simple proofreading. Look for your proper punctuation, look for the fact that you have correct capitalization, all those sorts of things. Okay. Good. All right. But now we're going to talk about how to improve your technical style. Right? Now, when we write technically, we want to try and write in the third person. All right, and you may see some journal papers out there that don't do this, but these are suggestions. But in the class, just so we kind of are all on the same page, and this is kind of best practices, I am going to treat this as things that you need to do. All right, so you're gonna have to write in the third person. So you're not going to use words like I, me, or we. You're going to use words like the authors believe that, or the investigators collected data at 6 Reynolds numbers. All right. Now, in general, what you want to do is avoid any of these words at all. So in the previous example, let's say you were writing the experimental setup. So one could say the authors of this paper conducted experiments at 6 different Reynolds numbers between 10,000 and 50,000. Now, that's okay, but the easiest thing to do would just be leave out any mention of the people at all and just say data was collected at 6 different Reynolds numbers between 10,000 to 50,000, whatever the numbers I said were. But you see how there I didn't have to say the authors or the investigators, and I definitely didn't use the word we, right? The other thing that we're going to want to do is always use the past tense, right? So the reason for that is the data that we're looking at took place, it happened, we did it, the week previous, and the only thing we can say is what happened to that data at that moment in time, all right? So we're always going to want to talk about past tense, when we're referring to our data sets. Right? As scientists, we tend to write run-on sentences, so just make sure that you are keeping your ideas pretty short. All right. Let's see if there's anything important here. Again, just proofread. The other thing is you always want to try and give some explanation of differences in the data that you expected to what you got from scientific principles. Okay. Do not use human error as a reason. Okay, that's like a high school sort of answer. All right, if you believe that there was human error involved and that's what did it, then really you should be doing it again. Okay, right? Human error is just this catch-all that students like to write when they don't have to think about a good explanation. All right, so no human error. I should never see those words in any of your writings. Okay. You want to make sure that you have all of your symbols identified. Okay, so if you're going to use the words, the symbols RE for Reynolds number, you should say that it stands for Reynolds number. A lot of the templates that you have to use are going to have a nomenclature section at the beginning, and that will take care of all of these, right? You always want to have your units, all right? Always, always, always. Data without units is meaningless, and a very, very common mistake in this class, all right? But you will be graded whether or not you are correctly describing the units everywhere. Now, in fluid mechanics, you might remember from the lecture, we learned about something called the Buckingham Pi theorem and non-dimensionalization. And we talked about why it's so important to describe everything in this non-dimensional fashion, right? It allows other people to use our data rather quickly. And so when possible, you always want to try and present your data sets in this class in a non-dimensional way, right? Another big mistake that I see is improper use of significant figures. All right, just because you punch two numbers, divide two numbers in Excel, and Excel spits out 10 digits of accuracy, you don't have that type of accuracy, right? And so I don't take this on, I don't actually go too crazy in making sure you have the exact correct significant figures, which you probably learned freshman year in physics lab. But in general, don't go beyond, let's say, 2 decimal places, 2 or 3 max. If I start seeing 4, 5, 6, then you'll start to lose points for that. All right. You should be having uncertainty with all of your data. Again, I will say that in the class, I will be a little bit lenient on that, but I do like to highlight that is important for your scientific work beyond this class, okay? But again, that could be very tedious, and just for brevity's sake in the course, we won't do thorough uncertainty analysis. All right, probably the single most important point that you should take home from today's talk is that when we write technically, we want to quantify, okay? Our job is not to try and convince people, right? It's not a persuasive essay. And so we want to stay away from words like, oh, the data was good, or the data looked reasonable, the data was acceptable. All of these don't give any quantifiable information, right? And so we want to make comparisons with numbers. We want to say, the data compared to the theory, or let's say the data collected differed from theory by 10%, right? 15%, right? Quantify, quantify, quantify. You don't have to persuade the reader that those are good, right? You just tell them the facts. You say the data was or differed by 10%, and then the reader gets to choose whether that's good or bad, right? It's not your job to be persuasive. All right. Every time you have a table or figure, there must be text associated with it. One issue I see is when students get to the results and discussion section, right? They just put like table, 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 and I call it a data dump. All right. You don't just put table, then figure, then table, then figure, then table, then figure with no text. All right. You want to interweave a table, text talking about that table, a figure, a text talking about that figure. All right. And very, very important, if you have a table or figure that you don't refer to in the text, it should be removed, right? The reason I say that is because if you don't take the time to describe that table or figure, then it must not be really important. And so if it's not important, then why waste people's time by including it in the document, right? So you must refer to all of your tables and figures with text. Right, simple things that you just be careful for, like the proper thing would be to put 0.02, right? You always include this leading zero. You don't just write 0.02. That's just grammatically incorrect, all right? when we're making figures, all right, it's important that you have to have either a title or a caption in the work. Your X and Y axes must have label with units in brackets or parentheses, all right? It's good to have tick marks and internal tick marks, so it's easy to read what the numerical values are off of the data, all right? And you have to have a legend, right? All curves must be labeled, and so the easiest thing to do is create a legend in MATLAB to do that, all right? So here's an example of a MATLAB figure. Okay, some of the important things here, again, we have distance here, but the units are in parentheses, time, and the units, right? Now here you see the data points are included as individual points, all right? Very, very important here. Analytical results must be plotted as dashed or dotted, and they do not use symbols. So if you're looking and you're trying to compare your experimental data, right, which are going to be points, to analytical data or theory, let's say, which is this continuous line. Now the reason for that is analytically, right, you have an understanding from an equation. So let's say you're looking at a free falling body or something. So you can figure out how far the distance has the distance with time of that free falling body. And so there's an equation for that, and this would be like the plot of that equation, right? This is not obviously because it's linear, but the idea here would be that since it's an equation, excuse me, at any time you wanted, right, you can plug in a number and you know what that value is, right? So you'd get a continuous line here. Now experimentally though, you are not collecting infinite number of data points, right? And so you want to show by highlighting that they are points, all right, where data was collected. So here I can see right away that this data was sampled at 1 hertz, right? Because I see a data point at 1 second, and then I see a data point at 2 seconds, and then I see a data point at 3 seconds, right? So right away, without even putting any text, the reader of this document can see that the data was collected at a frequency of 1 per second or 1 hertz, right? And so you get added info when we do that. Now, if you really wanted, you can connect experimental data with a line, but you must show the points, right? And again, I won't really grade you on this in the class, but all data should really include error bars for the uncertainty, all right? Now, technical reports, again, I want you to follow the format of the professional journals. You can use any professional journal template you want, ASCE, ASME, and AIAA. Those last two I do provide on Blackboard, as you had seen in a previous video. So when you're writing any written individual work or the full lab reports, you must use a template, all right? You're going to follow whatever template you are working with, but here are kind of the common things that you'll see. We'll look at an abstract, table of contents sometimes, table of figures sometimes, nomenclature is typical, introduction, approach, which I like to call experimental setup more often, a results and discussion section. Now, some journals you'll see separate that, or some organizations will have a results section and then a discussion. I think it's much easier to combine the two. So you show a result like a figure or a table, and then you immediately talk about that, not only what it shows, what it says, but also what it kind of implies to you. So I always combine, or I tend to combine, the results and discussion together, and then finally a conclusion section, and then sometimes you'll have an appendix. I should say you always have your references, and sometimes you'll have appendices if needed. All right, but let's get into each section now. The title sheet we're going to skip because we're not really going to use that with our professional or organization templates. But the first thing is the abstract, and the abstract should be short, all right, and it's just going to be like a quick paragraph, kind of get to the point. And it's often going to be the last thing you write. So you'd think, oh, the first paragraph here, the abstract, I should write it first. But really, you want to think about the entirety of the lab, what was done, and what were the main conclusions, and include them in the abstract. Right? It should be just one paragraph. It should state the significant conclusions and results. Again, you should be quantitative here. Okay, and it may be the only thing that's read, and so it has to be self-contained. Okay, there can't be any symbols in there that aren't defined. You can't refer to figures or tables that are within the body, right? You have to be able to understand everything by only reading the abstract, right? And you want to include the important experimental parameter ranges. So if you're running an experiment in the wind tunnel, you want to say, okay, data was collected between these Reynolds numbers, or these different flow rates, or these Mach numbers. Okay, you want to give, again, the overall experimental parameter. What was changed, right? Right? And again, if you have your theory, you want to be quantitative and give percent differences when possible. All right, always be quantitative, quantitative, quantitative. All right, table of contents, we'll skip that. Again, we won't have these often. Same thing for figures. Nomenclature, you're going to start with the English symbols first and then move on to Greek symbols. Introduction section. All right, the introduction section is going to be where we are doing our literature review and talk about the problem, right? So it says here we want to introduce the reader to the nature of the problem, right? Why are we studying this? And then it gets into the history and relevance of the experiment, right? What was known? What have other people done on this work? So the literature review, right? The general objective should be stated. Like, what are you trying to accomplish with your experiment, right? And you do not simply summarize the experimental objectives, all right? But you do talk about the problem and everything else, right? And you want to provide a guide for the readers what's going to follow. The experimental setup section, which is again sometimes called approach or methods or procedure. I actually don't like calling it procedure. I'm going to kind of cross this off for us. It's out of sync. Anyway, cross off procedure. I don't really like using that term because that gives the impression that you're going to write like a step-by-step pamphlet, which is not what you're going to be doing, okay? Please, 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 if there's the second most important thing other than being quantitative that you get from today is when you're writing an experimental setup, you do not list a play-by-play, meaning you don't say, okay, first the experimenters turned on the apparatus, then the dial was set to 4, then we did this, then we did that. I shouldn't hear any of those kind of time keywords. I shouldn't hear first or then or after this, okay? Please look at the examples from the journals online where you'll see what I mean, okay? You simply just say, data was collected between a Reynolds number range of 10,000 to 50,000, right? You don't say that you turn the machine on and all of that, all right? When we're writing the experimental setup, we want to talk about the apparatus itself. So the wind tunnel, what model of wind tunnel was used, what sensors. We're going to be using a lot of pressure sensors, hot wire anemometry, and you always want to give the make and model of those things. So as you're doing the experiments, take note of the make and model of the sensors that you are using. Right. When we get to the results and discussion section, again, I think these should be interwoven. So you're going to present data and then talk about it, right? One other small thing that's important is when you start the section, the first thing down shouldn't be a figure or a table. You want to start with words and introduce what's happening, and then have tables and figures after that, all right? But you always, always, always want to make graphs, all right? They're more important than tables. So sometimes, table is appropriate, excuse me, but more often than not, what's best is to take the information in a table that you may have generated while collecting data and turn that into a figure, right? It makes it easier to see trends if you can see the data plotted as opposed to just seeing a list of numbers, right? You want to try and be as concise as possible, all right? And as I mentioned before, you definitely want to refer to every single figure or table in the text, right? If you don't refer to the figure, right, it must not be important and therefore should be eliminated. Right? You want to evaluate the results to other studies or what you know, right? So a lot of our work, a lot of our labs are some fundamental ideas that can be found in your fluids textbook. So kind of referring to your textbook and seeing what you expect to what you got are important. Right? You also want to try and point out any of the limitations, so maybe you didn't run as many Reynolds numbers as you think are necessary, or maybe you would like to have used 2 different scale models, things like that, that could improve your results. All right, lastly, the conclusions. You want to have a discussion on the major findings, right? You don't want to bring in anything new, right? It's just a summary of what was done, very, very similar to the abstract, right? Be quantitative here, quantitative, 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 right? References, you only want to include references that you cited inside of the work. When you do your intro section, I'm going to require you to use your textbook as one reference and then one other journal paper, all right? One other journal paper. And you'll see when you get to that assignment, I have a list of some common or some highly cited journals in fluid mechanics that you can use, all right? But one journal article at a minimum, all right? A true journal article, not a random website, bobsaero.com, all right? That doesn't fly. A real journal article. Right? And then appendices, if you are wanting to supply maybe a MATLAB script that you wrote, maybe many calculations, huge tables, well, those shouldn't be distracting in the body of the text. They should be placed at the end in an appendix, okay? And that should be it in terms of technical writing. The only thing I do want to state is, a lot of this comes with practice, right? So read those examples that I put online, right? Give yourself a good reference to what's expected. And then I will always be open to reading your work prior to their submission. And I will give you feedback because it seems to be, the best way to go about this is to actually be able to correct individual people's work, right? So feel free to send me an email with a PDF of what you've written, and I will mark it up and get it back to you with changes that I think can improve your writing before you finally submit it. Okay, so feel free to do that. I encourage you to do that. I do think that it is the best and easiest way to improve your writing as quick as possible.